Right, so it's an average over lots and lots of people. So quick question, guys. If she lives, do they get money or do they lose money? How much do they get? 360. If she dies, do they get money or lose money? So it better be negative. Is it, how much do they lose?
100,000.
They lose 100,000, but they get 360. So 999, what'd you say? 640?
Because they already paid the 360.
Now, do you know the probability? Do you know one of these probabilities? Do you know one of them? Can you find the other one? Yeah, because they better up to 100%. So find that.
Really overthinking this for some reason.
Yes, Jake.
It should be 99,000.
Oh, sorry. My bad. My bad. I want to give her $1 million. Apparently. Yeah, Adam?
Wouldn't that number be negative instead of losing money?
Yeah, it should be negative. See that negative sign? Is that not there?
Oh, okay.
All right, so what's the probability that she lives, guys? Yeah, so what's the probability that she doesn't live? 1 minus that. Should I do that instead? Is that better?
Yes.
1 minus 0.999057, which equals 0.000943. Now, so then the expected value of x, the expected value, so this is, again, the expected value x is the expected value for one policy, assuming that you've done it, that you're going to do it thousands and thousands of times, it'll kind of even out in the long run, right? The expected value of this one policy is the value of the policy to you multiplied by the probability, plus the value of this, of this possible outcome multiplied by the probability. Yeah?
So wait, do you go to what x represents? Because
X represents the money that the value to the insurance company. How much is this person's policy worth to you? In the long run, how much you tend...
sorry, I didn't see the negative. Sorry.
Yeah. So it's going to be 360 times its probability, 0.999054, plus negative 99640 times its probability. And you guys get, what'd you guys get?
265.7.
265 point. Yeah, so they should make
65 cents.
roughly $265.70 per person that they have on this policy. In the long run. I mean, you got to remember, like, they also have other expenses, right? They have to pay commissions to the salespeople. They have to have an office building. They have to have workers' comp. They have all this other stuff. So it's not like they're, but they are making a fair amount. Which is why I don't have life insurance. Okay.
I mean, should one contribute?
A lot of people have life insurance because here's the thing: if you do die and you have a wife and children, and you're the sole money owner for them, or own money maker for them, then they're SOL if you're gone. So it was more prevalent back in the day when you had like one guy and he made all the money for the family. Like now you have like a wife and a husband, they both make money, so it's not as big of a deal. But maybe they both have a little bit of life insurance, so that if one of them dies, the other one doesn't have to sell the house and and move to a smaller house or whatever, right? That way you can kind of pay off the house and still be in good shape. Long-term life insurance is different. So my dad was looking at long-term life insurance, and that's where he's paying money every 6 months, so that when he needs to go into into a long-term health care, like, you know, those old people hospitals, what do you call those? You know,
Senior convalescent.
yeah, well, or care, like, severe,
Nursing homes?
well, not hospice, not quite that bad. Assisted care, yeah. So then it'll pay like, you know, $4,000 a month for 3 years or something like that. The thing about that is you got to run the numbers. And if you're going to live a very short, if you expect a kind of a shorter lifespan, like you think you might die like in your early 70s, that's a good deal. I plan on living to at least into my 90s, so it's not a good deal for me. It's just you have to kind of look at, you know, how much you're paying. All right, anyway, enough of that. So yes, generally speaking, if you're planning to die early, historically your family dies young, then it's a good thing. If historically your family does not die young, then it's not so good. Because you can take that same money you put into there, and you can invest it, and it'll grow, and then you can use that to take care of yourself. All right, enough of that. So let's go back to page 2. Page 2. Right here, we're at the kind of, not quite the top, but towards the top of page 2. Variance. Right, that's a little, the population variance, it's a little circle with the tail, squared. That's the variance. Standard deviation is the circle with the tail, not squared, right? So the standard deviation is the square root of the variance, right? Because the variance is the standard deviation squared. Remember, that's the relationship between the two. So if this is 9, this would be, standard deviation would be 3. Right, how do you get back and forth between them? Take this, you square root to get here. How do you get from here to here? You square this to get there. Right, if you have 3, then how do you get from 3 to 9? You, 3 times itself, you get to this one. Okay. The variance for these is, it's kind of a pain in the butt. It's every x value minus the mean squared multiplied by its weight, its probability. The problem with this is that it's very, very messy because your mean is almost always going to be a decimal. So you're going to take your x value minus a decimal, which is going to be a decimal. You're going to square that, so you're going to get even more decimals. And then you're going to multiply it by a probability. And probability is always between 0 and 1, so it's another decimal. So you're going to get even more decimals, right? And you're going to add them all up. It's really hard to keep track of all those. So it's a big, giant pain in the butt, and we just pretty much never use that. Instead, we use this kind of cleaner alternate program formula, which I think we talked about before with standard deviations. It's the computational model. So you take every x value, you square it, multiply by the probability, and then you add up all of those, and then at the very end, you subtract the mean squared. So we'll go through that, and I'll show you an example of that. But even that, I'm actually going to let you guys just use a calculator, but we'll go through one so you can kind of get an idea of what we're talking about. So here, I want to find the variance of this. Remember we found the mean last time? We took every value multiplied by its probability and added them up? And we got 3.5. Do you guys remember that vaguely? Good. So my mu is 3.5. All right, so here, every x value. So my variance, my sigma squared, is going to be every x value squared times its probability. So that's the first one. The next one would be 2 squared times its probability. The next one would be 3 squared times its probability. The next one would be 4 squared times its probability. And then 5 squared times its probability. And the last one would be, 6 squared times its probability. And then don't forget, we have to subtract the mean squared at the end. So this is going to end up being 1 squared is 1, so 1 sixth, 2 squared is 4, 4 sixths, 3 squared is 9, so 9 sixths, 4 squared is 16, 16 sixths, 5 squared is 25 over 6, and then 6 squared is 36 over 6, and then we're going to subtract 3.5 squared. If you do that, magically, you will get 2.9. If you square root that, The standard deviation will be 1.7. So remember, this is by variance. Standard deviation is the square root of variance. Good. So that's how we would do it with a kind of the by hand, kind of in a sense. But I'm going to let you guys, since none of this really is theoretically, you can't logic it out on your own, we're just going to use a calculator. So everybody, bust out your calculator, pull it up on your computer screen, your TI 8384. So everybody have theirs? Yeah. If not, then turn on your computer. You guys all have one, or do you have your computer up? Do you have your computer? Okay. All right. So this is how we're going to do it. Does anybody need to borrow one of these? I do have one. No. Okay. Is this on? Yeah. All right. So go to Stat Edit. So again, just to remind you. Turn it on, Stat, Edit, and then you get these lists. So to clear it, you go up to L2 where you're actually on the L2 and hit Clear, Enter. Not just clear, but Clear, Enter. If you want to clear this one, I would go up here and hit Clear, Enter as well. And then start typing them in. So 0, Enter, 1, Enter, 2, Enter, 3, Enter, 4, Enter. Whoops. Arrow up. If you make a mistake, just go back and overwrite it. Just enter it in and then go back and overwrite it. And then, so go ahead and put all your X's into list 1. I'll do it. And then put your probabilities into list 2. So put all those numbers into list 2. And again, if you make a mistake, just go back and overwrite it. Arrow back up and overwrite it. Okay, is everybody here so far? Does anyone have these input? Yes. Same thing?
Can I see something in the calculator?
Okay. So, does everybody have these in? Then, do your stat calc 1 bar stats. This is still one variable stats because we only have one x. We have an x and we have its probability. We don't have an x and a y. These are all still x's. In this case, these are all, what are they? They are number of colors in a call line is what these are. So these are the number of possible colors and the probabilities of each. So there's still only one variable. So stat calc 1 bar stats, but now we have a weighted mean. We have the x values and their probabilities, their frequencies. So you're going to put in L1, L2. If you have a fancy calculator, who has a fancy calculator? Hold up your fancy calculator. So if you have a fancy calculator, then if you have one of the later 84s, then it will give you 2 lines. It will give you one for values and one for frequencies or something like that. The second one's frequencies. Then you'll put the L1 in the top one and the L2 in the second one.
How do you put the L2 in the second one?
Okay, hold on, just arrow down. So let me show you what I mean. So stat, calc, 1 bar stats. I don't have a fancy one, it's just this. You guys see there's no extra things? So I'm going to do second L1, because I want the L1 to be there. And the comma, which is right above the 7, second L2. So then I have L1, comma L2. When I hit enter, it's going to give me all my stuff. If you have a fancy calculator, it will give you, anybody have it? Yeah. It'll give it to you separately. So you guys see Ulysses' fancy calculator, how it gives them separately? For your list L1 and list 1, and then in frequency list, use arrow down. So make sure L1's in that one, and it is. It's usually defaulted to L1. And then here you do the second L2, so you get the L2 there.
How do you get the best grade?
You get one or the other depending upon what calculator you have. So it's just a different version. So yeah, so just go down there and
Like the list is the best.
there.
How do you go?
It's different softwares. It's kind of like, it's different models, right? Like you could have a Toyota Corolla, but if you're 2009, it's not the same as a 2010,
What did you get for the answer?
2018. They have different things about them.
So I did it on paper
Yeah,
because
same
I
thing.
never used calculator, but I got 2.7, and I think that's what it has on.
All right. So everybody should have this, yes? Did everybody get that? If you didn't, check with your neighbors and see if they can help you. And if not, then I can try to help you.
Did you get that?
Yeah, I got 2.7 too, right?
Yeah, I got 2.7 too.
And I even did it, so I'm pretty sure right.
Yeah, and then this one. That's what I got. I got what you got. You got what you got?
Wait, what did you put?
1.59, 1.59, 3.79. Ah, nothing. 1.1, 2, 3, 4, blah, blah, blah. And then the next one. So how? Yeah.
Is anybody else still having an issue?
I got it. Here, let me see what you do. This is not wrong. No, do this one. So if you...
This is yours? Oh, you didn't use my data, you used your data. You're supposed to input the one I had on the screen.
That's one. Okay, because this...
Yeah,
'cause you didn't
so,
put the right number.
so you should have this. If you use the data, don't use the one, we're not doing your example now. We're not doing your lab problem. We're doing my problem, which is different. Does everybody see the difference?
You didn't
So
put
you're
the
supposed to
right
put
number.
in
You have to put the
this
1
one, this data here, not your data, this data. And then you should have the same thing as everybody else has, 1.58 as your mean.
But for the homework.
But I was wrong.
Okay.
You're right, please.
Exactly.
So in this case, it's theoretical, so it's for the whole population, so it's going to be population width. It's going to be mu and sigma. There is kind of an issue, which is that it doesn't have a mu. It only has, the best it can do is an X bar because mu just doesn't, I don't know, maybe it can't draw a mu, I have no idea. But anyway, your mean is 1.59, and your, see where it says sum of the x's? That's, you don't worry about that. Sum of the x's squared, you don't worry about that one. Sx, sample standard deviation, it knows it's not, because your probabilities all add up to only 1. You can't divide by 0. And then sigma x, that's your, so this thing here is sigma of your x values. So this is really sigma, because sometimes you'll have sigma of y values. You might have x's and y's. So it says this is sigma of the x's, of the stuff you put in the first one. So your Sigma, is that your variance or your standard deviation? Standard deviation. So how do you find the variance?
So scary.
You square it. So my x bar is 1.59, and my standard deviation is going to be 1.12. So that, we'll round these. 1.6 and 1.1. Now, where this came from? Okay, so standard deviation of 1.6. Sorry, standard deviation of 1.1 and mean of 1.6. And actually, this should be, this is really your new. This came from this example. Oh, shoot. Hold on. Let's get a reader. I had no read. Alyssa, go ahead and read.
A talk radio show has 4 telephone lines. If the host is unable to talk, an additional, i.e.
Yeah, example.
or is talking to a person, the other callers are placed on hold. When all lines are in use, others who are trying to call in get a busy signal. Should the station have considered getting more phone lines installed?
So we had our mean was 1.6, our standard deviation was 1.1. So we're going to go, here's our 1.6, we're going to go 2 standard deviations that way and 2 that way. This we end up with a negative number of some sort, right? Negative something. And over here we get 3.8. These are our usual values. 1.1, negative 0.6, I guess. So that means that most of the time we're going to get between negative 0 calls, basically, and 3.8 calls. These are our usual values. Does that sort of make sense? Let me try this again. People give me blank stares. So typically, most of our data lies within how many standard deviations of our mean? 2. So if I have my mean, and I go 2 standard deviations this way, I'll have 1.6 minus 1.1 minus 1.1, I'll get to a negative number. So basically 0, because you can't have negative callers. If I take 1.6 and go 2 standard deviations this way, plus 1.1 plus 1.1, I'll get to 3.8. So typically, I'm going to have between 0 and 3.8 callers. So I think 5 phone calls is enough? 4 phone lines is enough? Yeah. It should cover our typical values. So that's kind of what they were saying here. So the last thing I want you guys to do before we go on break is do your quiz problem number, or sorry, not quiz problem, your lab problem number 4. Find the mean, variance, and standard deviation using your calculator. Just do it using your calculator. You don't have to do the hard stuff. Just pop these into there, get a little practice doing them.